Okay, so maybe we can start. Today we are very happy to have Yiming Chen from another language institute at Stanford. He will tell us about phase of de Sitter density of states.
Okay, thank you. Thanks for the invitation. I'm very happy to be here. I'm sorry that I have to schedule my talk on Tuesday because there's going to be a workshop in Michigan tomorrow. I'm going to. So what I will be telling you today is a very recent paper written with Dr. Stanford, Haifeng, who's an excellent student at Stanford, and Zhenbin Liang, who's in Tsinghua in China. So let's begin. Oops, it's not working. All right. So over the years, we've learned a lot about black holes, and I would say many progress originated from the famous Bekenstein-Hawking entropy formula, which relates the area of the horizon of the black hole to the entropy of the black hole. And we've come to understand through this formula that the black hole really has a quantum interpretation that the area is really counting the microstates. Now, our understanding of this formula has benefited through both the UV string theory and also from the low energy Euclidean gravitational path integral techniques, the latter of which is what I would mostly focus on today. Instead of thinking about black holes today, we will move our attention to cosmological space-times, where in an expanding universe, since the universe is expanding very fast, a local observer, represented by this little biscuit man here, can only hope to observe a finite portion of the universe. Okay. So the observable universe will be bounded by a two-sphere, which here I just drew as a circle. And that also is called the horizon, namely the cosmic horizon, and also has an area. Because the cosmic horizon has many similarities to the black hole horizon, it has been proposed by Gibbons and Hawking that there's perhaps also an entropy associated with the cosmic horizon, which is usually referred to as the de Sitter entropy. Now, motivated by the black hole formula, a natural question and an important question to answer here is whether this entropy is also counting anything. Is it counting some microstates of some underlying quantum system? Now, the reason that in this talk we will be focusing on these low energy techniques is because despite tremendous progress in constructing de Sitter solutions in string theory, it has yet to really mature into a precise understanding of what these microstates could be in the de Sitter context. So here we will rely on more these low energy gravitational path integral techniques to try to say something about the meaning of the de Sitter entropy. So what is the gravitational path integral calculation that one usually associates with the de Sitter entropy? This was in fact also discussed by Gibbons and Hawking back in the days. Namely, if you consider de Sitter space-time in the Euclidean signature, it is just given by a sphere, an SD in d dimensions. Because the de Sitter space-time is expanding in the Lorentz signature, so if you weak rotate it, it becomes a sphere in the Euclidean signature. And semi-classically, if you evaluate the Einstein-Hilbert action on this geometry, you find that the Einstein-Hilbert action is equal to minus A over 4G, meaning that the gravitational path integral goes like e to the A over 4G, namely e to the S de Sitter. Okay, times some one loop factor, which we will soon go to. Now, the fact that this path integral gives you an answer that is e to the S has long been viewed as an evidence from the Euclidean gravitational path integral that indeed the de Sitter horizon has a similar state counting interpretation. Namely, if you do the path integral on the sphere, it's computing the number of states in some underlying microscopic system. Now, the starting point of today's talk would be that there is a puzzle about this. Namely, such an interpretation of this calculation as counting the number of states hinges on the fact that the one loop determinant is real and positive. Because at least for normal quantum systems, the partition function is always a real and positive number. But as was shown by Polchinski in 1986, he did a very careful analysis of the one loop determinant and found that, in fact, the one loop determinant is not real and positive. And in d dimensions, it comes with a phase that is I to the d plus 2. So a phase that depends on the dimension and is generally not positive. For example, if you plug in d equals to 4, you actually get a negative answer.
That's for just pure gravity?
This is for just pure gravity, yes. Now, given the success of applying gravitational path integral ideas to tackle many other problems, mostly involving black holes, it would be nice if we can understand this phase better, perhaps as the first step in trying to apply such techniques in de Sitter. Now, so the plan of my talk would be to try to explain to you some development over the last year about some further understanding of this phase. So I will first review to you Polchinski's computation of one-loop determinant. And the result here is that the phase is I to the d plus 2. I will then discuss, review to you an interesting proposal by Maldacena at the end of 2024, which he claims that by introducing an object which we now call an observer in the calculation, you find that the phase is modified to be minus I. And in the same paper, he explains that starting from this minus I, there is an additional step one needs to do. And in the end, the answer will be positive by including an observer in any dimensions. So maybe before that, let me just highlight that, in fact, after his first version of the paper, he updated his paper in April last year, and he changed the conclusion, saying that, in fact, by introducing an observer, the answer is always negative. So he found a subtle step in the computation, and after revision, the answer is always negative. That's where we entered the story, because we were very upset about getting a negative answer, because what would that mean? So we started to investigate this. First of all, we tried to reproduce this answer minus I by considering a more perhaps complete model for the observer, which I will explain that involves a charged black hole in the de Sitter space. So that's what I would then discuss, that by using charged black holes as an observer, you reproduce this minus I phase. Then I would discuss this last step, which is important to go from minus I to either plus or minus, which involves going from the Euclidean path integral to what we call the state counting partition function. And I will explain after a careful analysis that the final answer is always positive. So this would be the rough plan of the talk today.
We want to relate to Emil's question. So is it known if you add a bunch of fields, does the sign not change compared to the original?
Right. So in principle, this observer also comes from some scalar field, but it's a subleading. So if you just think about the one-loop determinant of a scalar field on the sphere, the dominant contribution will come from like very small loops of the wall line. But this observer idea, as I will explain, corresponds to some subleading contribution where you have a big wall line wrapping the equator of the sphere. Now, if you just add on top of that and consider one-loop, adding some other one-loop determinant of, let's say, heavy scalar fields, it wouldn't change the answer, as long as you are focusing on this subleading contribution with the one wall line wrapping the equator. You could further ask other questions like, what if you have two wall lines, etc. But let me not go into that now, but we can talk later.
So I guess whatever your resolution would be, you would hope that it would apply to several different theories, right?
Yeah. It wouldn't depend on the matter content of it. Yeah. As you will see, the ingredients are very simple.
That does seem a little bit odd, though. Like if I just consider a massive scalar field and I dial the mass, it goes from being some distributed thing with fluctuations that you would compute by some one-loop determinant to when the mass is very heavy, thinking about it as some heavy object that's just sitting somewhere, executing some geodesic trajectory.
Yeah. So the difficulty in that is if you consider very light scalar field, it's a bit hard to separate this subleading contribution, which has the geodesic wrapping on the equator, from like the dominant piece. So the discussion here would be in the limit where the mass is big compared to the de Sitter scale, that you can really isolate this piece where indeed there is an observer sitting there at the center of the static patch. And the claim is that piece always has a positive sign. But it's true, as you say, that there is this, you need to be able to isolate that piece. Okay. But let me perhaps explain more details and we can discuss more. So let me first review to you this computation of Polchinski, where this I to the d plus 2 comes from. So the starting point is the Einstein-Hilbert action, and we expand the action around the sphere background, which is our classical geometry. So we write the metric as the sphere metric plus some perturbation h mu nu. And for our purpose, let's focus on the particular mode, which is the trace part of H, also called the conformal mode, for which the action takes the form of a quadratic operator minus Laplacian square, minus Laplacian minus d. And importantly, there is an additional minus sign in front of the action. So this minus sign corresponds to the notorious conformal factor problem in Euclidean gravity, meaning that this H has basically the wrong sign action compared to a normal scalar field. So a normal scalar field, you will have a plus sign here, and most of the modes will be positive. But in fact, for most of the modes of this H, the action is unbounded from below. That's the so-called conformal factor problem. So we need to somehow, so maybe before that, so we can do a little bit better by using the symmetry of the background, which is rotation symmetry of ST, to decompose the modes of this conformal factor H into various spherical harmonics. Okay. So let's first look at the L equals to 0 mode, which is a constant mode on the sphere, for which the Laplacian term vanish, but you have this constant term minus d. So since that is negative, it actually cancels out this negative sign, and that corresponds to a positive mode. So the integral over the constant mode is actually convergent to begin with. The L equals to 1 modes are those that these two terms cancel precisely. So there are 0 modes at the quadratic level. And in fact, there are 0 modes for good reason, because you can show that they correspond to pure gauge. So these modes, in fact, can be generated by just a gauge transformation. In other words, they are not really part of the physical integral that we want to do. And the L equals to 2 until L equals to infinity modes, for all of them, the Laplacian term wins over the constant term, so they are negative modes. The integral are divergent at face value. Now, we need to have some prescription of dealing with negative modes. So for a given negative mode, the integral schematically takes the form of an integral wrong sign Gaussian. Now, as mathematicians, you would just say this doesn't make sense, but in theoretical physics, what we are trying to say is when you see such an integral, you will try to redefine the integration contour by weak rotate the contour of integral of x to the imaginary axis. So starting from the real axis, instead of integrating along the real axis, you weak rotate and integrate it along the imaginary axis. Now I won't go into detail about how to really make sense of this weak rotation, but long story short, you need to pick a consistent way of weak rotating. So you could either rotate it counterclockwise or clockwise. It's just a matter of convention, but we will pick one prescription, which for which the end result is that whenever you see a negative mode in the integral, after you weak rotate, it becomes a convergent integral, and it gives you a vector of minus I coming from this weak rotation. So the fact is minus I instead of I is just a convention, but we will stick to this particular convention and towards the end. So negative mode corresponding to minus I. Now, for our current problem at hand, there are infinitely many negative modes. That is the conformal vector problem. So the situation is a little bit analogous to the UV divergence in QFT, where you also encounter divergences. Here, the divergent thing is you have infinitely many factors of minus I. So in such situations, you should add counter terms to restore the predictive power of the low energy effective theory. So conceptually, that's what we also do here. The idea, which was first proposed by Gibbons, Hawking, and Perry, is that some counter terms should be added in the integration measure, such that if you weak rotated a whole field, namely if you weak rotated the entire conformal vector field, you will get no phase. Okay. Now, in fact, for space-times that we understand much better, say a thermal ADS or like a big ADS black hole, this kind of prescription gives very nice results because after you do this, you will get no phase in the end. Let me explain this prescription a little bit more explicitly. So formally, you can think of these as multiplying the original integration measure of the path integral by an additional factor, which roughly speaking is a factor that is a product over all the space-time points where at each point you associate with the additional factor of I. So why is this the same as saying that if you weak rotated the whole field, you get no phase? That is because if you weak rotated the whole field, namely a whole field means that you have 1 degree of freedom, namely 1 integral at each point of the space-time. In that, you will get a phase minus I to the infinity, or minus I to the number of space-time points from what I discussed earlier. And now multiply that with this additional counter term, this I to the infinity, you will get 1. Okay. So this might look a little bit formal that you're canceling infinities, but really this I to the infinity is just introduced precisely to cancel this minus I to the infinity. So it really should equal to 1 just by design. Now, I can now tell you where this Polchinski phase comes from. The subtlety is that in the de Sitter case, not all the modes of the conformal factor are negative. So as we said, the L equals to 2 until L equals to infinity modes, they are negative. So they require weak rotation to make sense of the integral. But not the L equals to 0 mode, which has already been positive to begin with, and also now the L equals to 1 mode, which are in fact pure gauge and they are not part of the integral to begin with. So that means you're already only weak rotating infinity minus 1, which is the L equals to 0 mode, minus d plus 1, which is the L equals to 1 mode. So L equals to 1 mode has some degeneracies as d, that is d plus 1. And that multiplied with this counter term additional factor that you added, I to the infinity, gives you I to the d plus 2. And that was how the Polchinski calculation goes, that in the end you get this non-trivial phase, I to the d plus 2 in d dimensions. Okay. Now let me move on to the Maldacenian's proposal. So the idea here is that motivated by some other recent discussion in the literature of the potential importance of observer in quantum gravity in the Sitter space, he studied the effect of introducing an observer in the sphere computation. Now, there are certain structures that an observer should carry, which are important for some things that would not play an important role in this discussion. For example, you hope that the observer carries some clock with some density of state, which is not very important for my discussion per se. All we need in this talk is to model the observer as a massive particle. And we will be focusing on this contribution where you have this massive particle wrapping the equator or a great circle of SD. So here I drew the case of d equals to 2, and then there is this red line representing the wall line of an observer. Okay, so we would just think of the observer as some object that you introduce into this Euclidean gravity calculation and see what comes out of it. At the end, we will try to comment a little bit more, like what is really the interpretation, etc. For now, let's just study this calculation with an observer included. So you immediately, it's very intuitive, you immediately see that the observer wall line also comes with negative modes. Think about the two sphere, if you rub a wall line on the gray circle, it's like rubbing a rubber band on the equator. It wants to shrink, it wants to slide off the equator. Okay. So you carry some negative mode, which on S2 there is one negative mode, but on SD there are d minus 1 different directions where the observer can slide off the gray circle. So that so one for each transverse directions, and that gives you an additional factor minus I to d minus 1. multiply that with the original factor of the sphere I to the d plus 2, you get I cubed, which is also equal to minus I. So that explains where this minus I factor comes from. Now, this is just some comment that the observer, by introducing an observer on the sphere, you break the isometry of de Sitter from SOD plus 1 into U1, which is time translation along the observable line, and some rotation SOD minus 1 in the transverse direction of the observer. And as we said, there are D minus 1 such negative modes associated with the observer. They are all kind of living in this SOD minus 1. For the I to the D plus 2 modes, you can also decompose it in terms of this U1 times SOD D minus 1 structure. And basically, you can see that you can decompose it as 2 plus D minus 1, where the D minus 1 living in its transverse directions, which in some sense are canceled out by the observer. And the remaining two phases are precisely two-dimensional. Namely, they don't really see the transverse direction. Okay, they are more in this U1 direction associated with the observer. So this is just to set up some we will use this feature later in the talk. Yes.
Can I say why you consider the gray circle storyline? Is it
a particular saddle point configuration.
I see. So it's some unstable saddle point.
Yeah, it's if you consider a massive wall line in Euclidean de Sitter, the saddle point corresponds to a wrapping the gray circle. And such computation have been also studied before. For example, if you compute the action of these, it gives you the correct Boltzmann way of nucleating an observer in a thermal de Sitter space. Good. And in the same paper, Molsena then explained how to go from this Euclidean computation to the density of state, or the state counting partition function. Because this step is particularly subtle, we will delay this part of the discussion towards the end. But it's important because it decides whether you get a positive or negative answer. In the same work, it was also suggested that instead of introducing an external observer, one can consider a small charged black hole in the theory, which is kind of an intrinsic observer in the gravitational theory as an observer. So we will follow this suggestion. That's what we will study in the next part of this talk. So the idea here is that instead of considering this observer in the probe limit, we will study much heavier observer like a charged black hole in the de Sitter space. Now, the first thing you might want to consider is just an uncharged black hole in the de Sitter space. But an uncharged black hole, in fact, is never in thermal equilibrium with the cosmic horizon. It will evaporate. So it's not a very good model of an observer that it lives for a very long time and so on. A good model for an observer that lasts for a long time will be a black hole in thermal equilibrium with the de Sitter horizon, which you can achieve by considering charged black holes in de Sitter, either electrically charged or magnetically charged. So for convenience, we just studied magnetically charged black holes because for electric ones, there are some additional factor of I's when you rotate into Euclidean signature. We just studied magnetic ones for convenience. Now, this is the metric of the magnetically charged black hole in 4 dimensions. So you have the standard black hole metric, which depends on 2 parameters, the mass and the charge of the black hole. And then there is also a gauge field, which for the magnetic black hole lives on the 2-sphere, you see the phi direction that is proportional to the charge. Now, let me tell you a little bit about these black holes in the de Sitter space. You can ask where can these black holes be? Where are the valid black hole solutions in the 2-dimensional plane of Q and mass, the charge and the mass? Now, the black hole solutions turns out only exist in the shaded region. So this shaded triangular region, which also looks a little bit like a shark fin, That's why this, if you rotate it 90 degrees, it looks like a shark fin. That's why this picture is also called a shark fin diagram. And it only exists in this shaded region. But the solutions where the black hole is in thermal equilibrium with the de Sitter horizon are in fact only exist along the solid lines. So there are two branches of such black holes. One branch is the so-called lukewarm black hole that kind of starts from very small mass and charge, and then you can increase the charge together with the mass. Eventually, it reaches some maximal charge. And then there it joins with this other branch of black hole that is called the charged Nariai black holes in de Sitter. Two branches merge at this point, and then above that, you only have charged Nariai black holes, and then you reach a maximal charge, which is the so-called ultra-cold limit. Okay, so the question that we will now study is what are the phases of the gravitational path integral on these only solid lines for these black holes. Also, let me mention that only the lukewarm line is stable. So for the charged Nariai line, is actually known to be unstable. If you perturb it a little bit, it will start to evaporate towards the lukewarm line. Above the charge 1/4, all the black hole solutions are stable. So to study the one-loop determinant of these non-trivial black hole solutions is in fact very non-trivial. And to simplify the problem, we will study the phase in a truncated model. We truncate this analysis in two ways. One is that we set the gauge field on shell and do not consider the fluctuations of the gauge fields. This is roughly because we expect all this interesting phase to be residing in the gravitational sector, and there are no instabilities associated with the gauge field sector. And another truncation is that we dimensionally reduce to 2 dimensions. Namely, we only keep fluctuations in the S-wave sector. This is justified for the brief comment I made earlier that the transverse modes are kind of cancelled out between the observer and gravity. So the remaining non-trivial phase, you expect them to be living in the S-wave sector. Now, both of these are arguments which are not rigorous, but they have been verified with full higher dimensional computations, which appeared later than our paper. So for the charged Nariai black hole case, it's simpler, which this paper is already out. They did the complete higher dimensional computation, and the answer agrees. For the lukewarm black hole, which is much more complicated, is some work in progress, which is hopefully to be appearing soon. Good. So let me discuss a little bit about the dilaton gravity truncation. So you start with the 4D metric. You, as usual, write down these ansatz of some scalar field, which we call the dilaton, multiplying the transverse 2-sphere. And then there is also a 2D part of the metric, which we will keep. And by doing the dimensional reduction, you get the following dilaton gravity theory, which has the usual term of the dilaton coupled to the Ricci scalar phi times r, but with a non-trivial dilaton potential that depends on the charge of the black hole that takes this particular form. Now, first thing you will try to do is to try to identify the solutions in the 2D dilaton gravity theory, which match onto these solutions in the 4D theory. So given a dilaton potential like this for a generic charge, there are in general 2 solutions for charge smaller than 1/4. One solution is a charge in a Nariai solution where the dilaton is just a constant on the 2-sphere, and the background metric is in fact just a round 2-sphere. That's why it's particularly simple. And that corresponds to a solution where the dilaton takes the value where the dilaton potential crosses 0. And then there is also the lukewarm solution where the dilaton varies from phi b at the black hole horizon to the phi c at the cosmic horizon. So in terms of in this plot, it corresponds to the shaded region. And basically, this shaded region is determined by that the integral from phi b to phi c of the dilaton potential should vanish, and also the value of the dilaton potential on the 2 ends should be opposite. Okay. So these details are not particularly important, but here is just to show you there are these concrete dilaton gravity solutions you can consider. Now, the next step is to study the quadratic action, where we will work in a conformal gauge, meaning that we will keep the dilaton perturbation as some classical solution plus vol phi written here, and then the perturbation of the metric will parameterize that as the conformal factor. Namely, we write the metric G as e to the 2 omega times the classical solution. Now, it's a straightforward exercise to try to work out what the quadratic action is. Takes the following form. So basically, it's a coupled problem of two scalars, phi and omega, with the following 2 by 2 quadratic operator. So the problem essentially by this step boils down to a QFT problem with two scalars. Although it's not a very straightforward problem to analyze, let me explain a little bit why. So one comment is that this conformal factor problem remains in the 2D gravity theory, which you can easily see by going to the UV, namely we look at very short distance modes on the two sphere. In that limit, we can ignore basically all the terms in this quadratic operator, which depends on the potential, but focus on the derivative terms. So in the UV, it basically is this Laplacian on the off diagonals. So then if you try to diagonalize this matrix, you find that in the UV, omega plus phi approaches positive, while omega minus phi approaches negative. Okay. So there are infinite many negative modes in this problem as well. Away from the UV, what makes this problem difficult is that away from the UV, the two fields are coupled. So it's much more complicated than the original sphere, which you can there's only this single field conformal factor, which you can then just simply weak rotate. Here you have these two scalar fields that are kind of tangled in some way, and it's not clear how to do a simple weak rotation that will make the action positive, definitely. In particular, how to really count the number of negative modes and compare that to the, let's say, the number of space-time points or the number of modes in a single field. Let me maybe skip over this, but this slide is just saying that there are some analytic aspects you can try to understand about this problem by understanding that it has some residual gauge modes, similar to these gauge modes that we also discussed in the sphere case. So they corresponds to some conformal Killing vectors that are not Killing vectors on the background. So they will show up as zero modes in the spectrum. So this you can understand analytically, but I won't go into detail of this. This is just a number of zero modes of the quadratic problem for various branch of the solutions. Now, this problem, even though you reduce it to this quadratic problem of two scalar fields, it's not very easy to solve analytically. But in a particular limit, which is something nice things happen, you can in fact solve it analytically. So that is the so-called ultra-cold limit. As usual, simplification usually happens when you take some parameter to be very extreme. Here, it involves taking the charge to be almost the maximal value. So what happens here is that basically, if you rescale the dilaton and the metric in some suitable way, you find that the action just becomes, for the dilaton, the potential just becomes quadratic in this limit, in this ultra-cold limit. Then you can simply integrate out the dilaton field. Then it gives you a problem of a pure 2D gravity theory, but with an R-square potential, R-square action. Okay, so this is a gravity theory you can try to then solve exactly and understand what the phase that comes out of it. So I won't discuss that in detail, but you can find more details and some further comments about the ultra-cold limit in the paper. So for more general charges, like in the most parts of this diagram, mostly along the lukewarm branch, analytic approach are not available. So one needs to resolve to some numerical approach to solve this quadratic problem. Now, in numerical approach, you can solve the spectrum of the quadratic problem, but the challenge is how you count how many negative modes there are and compare that with the counter term. So ideally, one would like to have a way to implement this factor, multiplying each space-time point with a factor of I reliably. So we explored a technique that is some kind of pragmatic approach where we discretize the space-time with a finite mesh. So here we have some two manifold, and we simply discretize the two manifold with some finite lattice. And then once you've done that, you can study the spectrum of this quadratic operator on this finite lattice. And the final answer is unambiguous, because on the finite lattice, there is an unambiguous meaning of how many points there are. So in the counter term, you will have this factor of I to the number of points in the numerical problem. And also in the numerical problem, you can count how many negative eigenvalues that you get. From those, you get minus I to the number of negative modes. So the product of these will be the final answer. And this turns out to work pretty well. It's fairly robust. It doesn't really depend on what kind of mesh that you put on the sphere. The answer that you get is always the same. So here, let me just show you the final answer. For the lukewarm line, you find that the phase is always I cubed by doing this analysis, and that interpolates correctly to the small mass limit, where we go back to this probe picture that Maldacena had of a probe particle in de Sitter, which is minus I equals to I cubed. And our result extends his analysis into this fully backreact regime, where the black hole is very, very heavy, could be very heavy in de Sitter space. For the charged Nariai with charge greater than 1/4, you also get the same phase. But for charge that is smaller than 1/4, you actually get a different phase. You get I to the 0. But that's not a surprise, because as I said earlier, the charged Nariai case is unstable, because if you protrude it away from that line, you would evaporate towards the lukewarm line. So there are some additional negative modes associated with the charged Nariai lines. And that correctly accounts for this difference between I to the 0 and I cubed. So that is also explained. Actually, this is just what I just said. So first of all, the result we got agrees with existing results, both with the probe limit of the lukewarm line, and also people have also studied the uncharged Nariai solution, where they've also computed the phase of the 1-2 determinant. So that checks out. As I said, this transition from I cubed to I0 comes from an additional L equals to 1 multiply of negative modes. Now, 0 modes, which I didn't discuss in detail, also match with the analytic expectations. Okay, so the benefit of now having this dilaton gravity model is that we can kind of not just having the answer, but also open up the answer a little bit and try to see where this I cube really comes from in the computation. So to do that, I would discuss briefly this mini integral model which reproduces this I cube phase. Okay? So roughly speaking, one way to think about the sphere computation is to first divide it into the whole part of the geometry and the de Sitter horizon part of the geometry, and in the last step, join them together. So the inspiration here is very roughly, you might hope for a description of this black hole coupled to the de Sitter horizon as two quantum systems. Perhaps one is a black hole quantum system, the other is some mysterious de Sitter horizon quantum system, and then the two systems are coupled together. So that's roughly speaking what we have in mind here, although this quantum interpretation is not going to be essential. So you have an integral over the phi b, which roughly speaking, you can think of that as the energy of the black hole. You also have an integral over the energy of the cosmic horizon. So there are some action, and then you glue these two systems together along with at a boundary that has length L and where the dilaton takes the value which we call phi group, phi g. Okay. So this mini integral, three-dimensional integral, is another kind of brutal truncation of the full problem, leaving only three integration variables in the end. But we will see it captures some essential features of this phase. Now, you can try to calculate, look at what this integral really look like exactly. The idea is here, let me unpack this expression a little bit. So we expand these three variables around their saddle point values. So you have integral of delta phi b, delta phi c, and delta L. Let's look at the action and look at what kind of terms that you have. You have a term which is involves the integral over the energy of the black hole and with a coefficient that is positive. So these, roughly speaking, this positive coefficient corresponds to the statement that the black hole has a positive specific heat. And the integral over the cosmic horizon energy has an opposite coefficient that has an opposite sign, and that is this related to this common statement that you hear that the de Sitter horizon has a negative specific heat. And the two energies are coupled through this integral over the delta L. This is kind of like similar to integral of delta beta. And then there is this additional integral. Now let's try to do this integral in the following way. Let's first integrate out delta phi b and delta phi c and see what we get. So recall that delta phi b is a stable integral. So integrating over it gives you no sign, while delta phi c integral is unstable. So integrating it over it actually gives you a minus I. So that's how we can reproduce this phase minus I or I cubed from this calculation. And after you do the integral, the remaining integral for the delta L variable is stable. It's a stable integral with a coefficient that is positive. So a further integral of a delta L does not give you additional phase. Namely, in the end, this mini integral gives you a phase minus I, which is equal to I cubed. Mathematically, let me tell you that the structure here is kind of similar to the case of a flat space black hole. It is well known that there is a physical negative mode, which is different from the de Sitter case. This physical negative mode is outside the conformal factor, conformal mode sector is in the so-called transverse traceless sector, which roughly speaking corresponds to the horizon size or energy of a flat space black hole. It corresponds to the negative specific heat of flat space black hole. And people in the past have also used this kind of mini integral, toy integral, to capture this negative mode. In other words, if you try to compute the partition function of 4D structural black hole, you will have an integral over the energy, but the energy, since the black hole has a negative specific heat, is diverging. So you get a minus I in the answer times a factor that is convergent, or the Gaussian suppression is the right sign for the beta variable, for the length variable. So here I just want to highlight that this mathematical structure here is fairly similar to what you will get in the flat space black hole case. However, this mathematical similarity hides the fact that in the flat space black hole case, we have infinite +1 negative modes. Namely, apart from all the conformal factor, you have an additional negative modes. While in the de Sitter case, even though in the end you get the same phase, what really happens is that you have infinite -3 negative modes. The difference is 4. As you know, I to the 4th is equal to 1. So at the level of the phase, you don't see the difference. But I just want to highlight that there is kind of this I to the 4th lurking around in the calculation, which I will comment a little bit more on later. So let me now use the remaining of my time to tell you this particular subtle step of the going to the state counting partition function from this Euclidean calculation. The idea here is the following. So in quantum mechanics, if we want to go from the partition function to the density of state, you will try to do an inverse Laplace transformation of the partition function, where you multiply that by e to the beta e, and then integrate beta along the imaginary direction, okay, divided by 2 pi I, and that gives you the density of state. The reason you want to integrate beta this way is because in this way, the beta integral becomes a delta function integral. So you can imagine expanding 0 beta as a sum over e to the minus beta times en, and then the integral over beta will pick out those terms where en is equal to e by a delta function. So this is this imaginary contour of beta corresponds to a delta function integral imposing the energy to be e. So in de Sitter, I didn't emphasize, but in principle, for this observer problem, you want a similar integral, which imposes the Hamiltonian constraint h equals to 0 along the observer wall line. Okay, so in other words, you have maybe let me draw a picture. So you have a wall line here, and then in principle, along the observer wall line, as you continue to the Lorentzian signature, you want to impose that the h observer plus h bulk should equal to 0, and that should also be implemented by an integral over the length of the wall line along the imaginary contour, similar like this. This is a different contour compared to the Euclidean gravity calculation, where instead, in the Euclidean kind of calculation, you will just integrate in length variables along the real axis. So this is where this last factor of I comes from. This difference was emphasized by many authors in the past, and for all the current context was discussed already in this paper by Molosina. Clearly, this has to do with the last factor of I, but different treatments, in fact, lead to either a negative or a positive answer. So it's kind of quite consequential that how you treat this last integral. So let me try to explain a little bit to you what's the we think is the correct way to do the integral. So let me first discuss why in the updated version of Molosina's paper he got a negative answer. So in the case of de Sitter coupled to an observer, namely this model over here, one imagines integrating over everything else apart from the length of the observer wall line. So you imagine you have integrating over everything else apart from the wall line. So the last integral you want to do is this integral, similar to the toy integral that we had for the lukewarm black hole, or you can view our lukewarm black hole case as a verification of this structure that was introduced in Molosina's paper. In other words, you have already a factor of minus I out front, and then the integral of beta is convergent. On the other hand, what you really want to do to have this state counting interpretation is to impose the Hamiltonian constraint. Namely, you really want to integrate over delta beta along the imaginary direction, as I emphasized. So you kind of want to undo this integral of delta beta, rotate it to the imaginary axis and integrate it along that contour, okay? But now the issue is that even though the delta beta integral along the real axis is convergent, it's in fact divergent along the imaginary contour, right? Because if you weak rotate it, the convergent integral becomes a divergent integral. And by our rule, for each convergent integral, you should get a factor of minus I. So that is the origin of this -1 that was in this updated version of his paper. So minus I squared will give you -1. Now, one thing that we noticed is that the same kind of manipulation, if you apply that for the flat space black hole, would in fact also lead to a negative density of state. So let me remind you that already we discussed earlier that if you look at the canonical partition function, canonical ensemble partition function, it takes this form minus I times a normal Gaussian. But then if we want to go to the microcanonical example, by doing an inverse Laplace transformation, you'll also try to integrate over beta along the imaginary axis. And if you follow the same logic, you're going to get an answer that is negative, which is very troublesome because we think we understood flat space black holes are normal quantum systems, and it should have a positive density of state instead of a negative density of state. So the resolution of this mathematical puzzle is that really this is a situation where the order of integration actually matters. Okay? Usually we don't care that much of order of integration, but here actually it matters a lot. Now, the idea is that to get a reasonable answer, even in the flat space black hole case, you should pause the integral over the energy and perform the integral over beta along the imaginary direction first. So let's unpack this expression. So here what I wrote is basically I didn't do this energy integral. So I have a double integral of energy and beta with e to the beta E0, which comes from the inverse Laplace transform. And then in the Z of beta, you have the Boltzmann weight and the entropy term. Now you see, if you first do the beta integral along an imaginary direction, the beta integral achieves what it is supposed to do because it imposes a delta function. It imposes that the energy is equal to E0, inserted this delta function E minus E0, and then the integral over the energy is in fact perfectly convergent. There's simply no divergence involved, and then you get a positive density of state. So notice that in this way of doing the computation, there is no contour rotation in fact needed. And we think that this is the correct way of doing the integration because only in this way of treating the beta integral, it really achieves what it is set out to do, meaning that it imposes this delta function. So the beta integral manifestly gives the delta function. This is what it is meant to achieve, namely fixing the energy or imposing the Hamiltonian constraint in the de Sitter context. The importance of integrating over beta along the imaginary direction before doing other integrals, such as the energy integral, was also previously emphasized in the literature, such as by Damarov in his papers. They like to think of these as kind of emphasizing a more fundamental integration contour for the gravitational path integral that is called the Lorentzian path integral. Which essentially in this context means that you should first integrate over this beta or the period of the time along an imaginary contour. And do that integral first before you integrate over other things. So we propose that in the Sitter you should apply the same prescription. So let's look back at this integral that we had. We should really first integrate over the delta L mode, where upon integrating over the imaginary contour, you just I'm not seeing your nice screen. Oh, it's on the computer. Okay. So integral over that just says that there's a relation between the black hole energy and the cosmic horizon energy, which is an analog of this Hamiltonian constraint that I was mentioning earlier. And after you do that, the integral is just fully convergent. There's no funny minus i's anymore. And it gives you a positive answer for this final state partition function. In our paper, we illustrated this idea with a few more different examples, including wall line observer in the Sitter 3 and perfect fluid observer in the Sitter 4. So you could, if you're interested, I would be happy to tell you, or you can check the paper for more details. Okay, let me summarize. So Molosina's proposal of curing this old Pochinski puzzle of Pochinski phase with an observer seems to really work as originally intended. But one finds a positive answer in the end, suggesting a state counting interpretation. So this seems to align, maybe let me say this first. It is tempting to interpret this positive result as suggesting that observer somehow plays an important role in a quantum mechanical description of de Sitter space, at least in these kind of problems associated with cosmic horizon. The fact that observers might be important might be pretty upsetting, but on the other hand, it also is kind of natural because the cosmic horizon, which is different from the black hole horizon, basic difference is that it's only specified once you have introduced an observer. So perhaps it's not that big of a surprise that an observer will somehow play an important role in assigning the cosmic horizon some kind of entropic interpretation. Now, there has been many other recent developments coming from various different angles of trying to say that observers are important in closed universes and de Sitter space. One particular thread of development involves this importance highlighted by papers by Witten and collaborators, highlighting the importance of having an observer to formulating observable in de Sitter space-time. Now, I should say that the connection between all these different approaches and this particular sphere computation is not entirely clear at the moment, and I think it's an important question to try to relay them and to study more problems. Another technical issue I want to highlight on my previous slide is that as opposed to the ADS and black hole story, where simply by recrotating the conformal factor, you get a positive answer, the positivity of the de Sitter answer seems to depend on elementary mathematical identity, namely I to the fourth is equal to 1. So the fact that you need to use this additional identity instead of just finding one manifestly is a little bit unsettling. It might suggest perhaps there are further modifications of the computation which could remove the phase completely, or perhaps this additional phase points to some further mystery or misunderstanding. We had some private discussion about this phase, which eventually didn't go into the paper. I'll be happy to tell you about in private, but I think it's an interesting question to ponder on this identity a little bit more. Okay. Now, so what next? So what should we do, right? After you find the sphere is positive, what's the next step? I'm cautiously optimistic about this whole idea of introducing observer in this sphere partition function. I think one should follow this idea to its absolute logical conclusion. We should start study many more problems in de Sitter space with the presence of an observer, and revisit many old ideas and see whether this additional ingredient has the potential or not to resolve these many old puzzles about de Sitter. So here I just listed some possible questions one can think about in the future. And in fact, we are trying to, we have some work in progress in exploring some of these ideas. One kind of questions is, what if you study more complicated observables? Let's say, if you, along the wall line of the observer, you insert some additional operators, say you measure some 2-point functions. Do these kind of 2-point functions suffer from the Polchinski phase or not? And a more advanced questions which could relate to this interesting black hole discussions is that in the black hole context, much has been learned from asking fine-grained questions such as whether 2-point function decays to 0 at late time. So you could ask, similarly in the de Sitter context, if indeed introducing an observer gives you a quantum mechanical system, is it a chaotic quantum system or what are its features? So you could probe that by asking, do 2-point functions decay to 0 at late times? And we envision that perhaps for many of these kind of questions, space-time wormhole effects, which have played an important role in ADS, will also play an important role in the de Sitter context. Here I just drew a very inspirational picture, but we are trying to investigate this a little bit more. And with this, I'd like to thank you for your attention.
Let me try to make sure that I understood. So when you were computing the one loop determinant, you basically expanded it around the black hole solution. And then basically computed that one loop. But for the, say, just the particle like observer, I would have thought that you would have done first the pure gravity one loop, and then you have this particle expanded around this gray circle title.
Yes.
Right? But then you had a picture where, you know, as you decrease the charge, you actually reach the particle case. But then what I'm confused is that why is it that you are not taking the product of the two one loop determinants, one around the original background and then the other around the black hole background?
So strictly speaking, so Molosina's calculation is in a probe limit where you can think of the sphere and the particle as separate. In other words, you are neglecting any back reaction of the observer on the sphere. So that's why the one loop determinant, you can view it as the product of two things.
I see here it's already.
In our case, you really can't separate out the one loop determinant into like a product of two things because the black hole is like heavily back reacting the space time. So you really have to do a full calculation of the one loop determinant on this non-trivial geometry. So that I view that as an improvement of the original calculation.
I see.
Right. There are no more questions. Let's thank you again.